Welcome to Chapter 9. Today, we'll be looking at hypothesis testing. The objectives of this chapter is we'll be able to formulate null and alternative hypotheses for applications involving a single population mean and proportion. We will also look at two types of errors, which is a type 1 error and type 2 error. In addition, we'll look at how to correctly formulate a decision rule for testing a hypothesis. And we'll look at how to know how to use the test statistic, critical value, and p-value approaches to test a hypothesis. So we'll basically look at the critical value approach and the p-value approach. And we'll look at how to compute the probability of a type 2 error. For this class, we're going to skip this step. We'll just talk about the different types of errors, type 1 and type 2. We will look at how to compute type 2 error. All right. Now, so let's start section 9.1. What is hypothesis testing? What is an hypothesis? Now, hypothesis testing is an application of statistical inference. Now, this is similar to confidence interval. So in this chapter, in confidence interval, we looked at the population mean and population. We looked at the mean and to estimate the mean and proportion. The same thing we're going to do here. Now, testing, so by hypothesis here, we want to test whether or not a claim is valid. So we're trying to test whether or not a claim is valid. Now, what is a claim? Now, as you will see, a claim is a sort of a statement that can either be true or false. Okay? So this hypothesis testing is performed in many industries. So it's a major part of business analytics. This really is the high point of all that we've been doing from chapter 1. We are at the zenith of all the topics so far. So this is really where we are trying to get to from the very beginning, how to conduct an hypothesis test, how to make a decision based off whatever research or business ideas that you have formulated and you would like to test. So we'll look at several examples today. So this year so hypothesis testing provides managers with a structured analytical method for making decisions about population means, proportions, as well as computing different populations as well. How do we formulate hypotheses? So let's start thinking about this. How do we formulate hypotheses? So take, for example, we're testing the status quo, and we have a statement here that says the box of cereal has a mean fill of 16 ounces. So that could be true or false. That's a statement. So here, our claim here is that the box seal, what's our claim? Is that the box cereal has a mean fill of 16 ounces. So we are saying that the claim here is that the mean is equals to 16. Okay? And what's the opposite of this? The opposite is that the mean is not equals to 16. So whenever you're given a claim, any statement, you want to put it in terms of the claim. What's the claim? And what's the opposite of the claim? So with these, we'll be able to determine what type of hypothesis they represent. So there are generally two types of hypotheses. you would hear me talk about the null hypothesis, which is a statement of equality, and the alternative hypothesis. There are 6 different symbols we're going to use: equals to, greater than or equals to, less than or equals to, less than, greater than, not equals to. Whenever you see these 3 symbols, equals to, greater than or equals to, less than or equals to, that would always go to our null hypothesis, which will represent as H of O. Ho, 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 ho. And then our alternative hypothesis would have the symbols, the less than, greater than, or not equals to. And we'll use H of A. Sometimes in some text you see H of 1. But I like H of A, so it reminds me of Christmas, my favorite season. Ho, 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 ha, ha, ha. All right, my friends. So with these, we can see clearly that the claim here would be the null hypothesis, and the opposite here would be the alternative hypothesis. So that's how we're going to state it. So that's how we formulate this. Let's look at another example. So testing a research hypothesis. So here, our claim here is that Goodyear's tire will last longer than 60,000 miles on average. So that's the claim that's going to last. So we state our claim. What's the claim? So the claim is that mu was going to last longer than 60,000. So that means we're saying mu is greater than 60,000. If that is the claim, then the opposite will be mu is less than or equals to 60,000. So first write the claim and then write the opposites. And now once you've done this, you can see that the opposite here this time around will be the null hypothesis is the opposite, and the alternative hypothesis is the claim. So when formulating your hypothesis, I would like you to express it in terms of the claim and opposite first before you determine which is the null hypothesis and which is the alternative hypothesis. Another example. So testing a claim about population this time around, or about population. So we're giving here that the mean waiting time in a medical clinic is less than 15 minutes. So our claim here, this time around, our claim is that the mean waiting time in a medical clinic is less than, mu is less than 15. So the opposite will be mu is greater than or equals to 15. So looking at this, the opposite is the null hypothesis, and the claim is the alternative hypothesis. Now, one thing I would like you to take note here is that in order to prove a claim, if you want to prove a claim is right, it should be stated as the alternative hypothesis. So if you want to prove a claim is right, it should be stated as the alternative hypothesis. Okay? So you should state, so this is our claim, that's the alternative hypothesis. This is our claim, that's the alternative hypothesis. This is our claim, it's not, so you wouldn't want to state it this way. So if you want to, in order to test, to prove that the claim is right, it should be stated as the alternative hypothesis. So that's really how to formulate your hypothesis. So let's move further. So there are, so 2 hypotheses are formed. Like I mentioned, we have the null hypothesis, which is H of O, and the alternative hypothesis, which is H of A. Now, the null hypothesis and the alternative hypothesis combine to cover all possible values for the population mean. Okay? So the null hypothesis must be stated as either equals to, less than or equals to, greater than or equals to. So that's how you state the null hypothesis. The null hypothesis and alternative hypothesis are always stated in terms of the population mean. It's always in terms of this population mean. So for example, this is a well-formed hypothesis. This is wrong. This is right. Okay? So you always state your null and alternative hypothesis in terms of the population mean. Okay? Good. All right, so hypothesis testing logic. If the sample mean is inconsistent with the null hypothesis about the population, the null hypothesis should be rejected and the alternative hypothesis should be accepted. We get to see what all that means. So we're going to have a distribution like this, and we have the rejection regions and the fail to reject region. So if the sample mean is inconsistent with the null hypothesis about the population mean, the null hypothesis should be rejected and the alternative hypothesis should be accepted. This will make sense when we look at more examples. So by inconsistent, we mean that the sample mean is significantly different from the population mean. So what that means is that if I have this, just for fun, just want to draw another bell-shaped curve, not really looking like a bell-shaped curve. Let me erase this and draw again. Okay. So what I'm saying here is that if this is a rejection region, so if the sample mean is somewhere around here, this is the sample mean, and it's significantly different from the population mean. So the population mean, say, is within this range. Remember when we did confidence interval, we computed a range. So let's say this is the range, and our true population mean is within this range. Now, if the sample mean is significantly different from the population mean, that the difference cannot be it means that the difference cannot be attributed to sampling error. So in this case, this is the rejection region. So the null hypothesis should be rejected and the alternative hypothesis should be accepted. All right. Now, we've talked about, so there are three types of hypothesis tests. So we have the two-tailed test. Now, the two-tailed test means that we have our rejection region at both tails. And then we have a one-tailed upper tail test. And so it's a test in which the null hypothesis can be rejected if the sample mean is inconsistently larger than the hypothesized population mean. Now, the one-tailed upper tail test is also known as the right tail test. So it means that our rejection region is on the right. So this shaded area would be our rejection region. And then we have the one-tailed lower tail test. And this will look like this. And our rejection region is to the left. We also call this the left tail test. Or it's also called the one-tailed lower tail test. So I'm trying to ensure that you're not confused when you hear this different terms. So I might use these as, I would say this is the left tail test. Left-tailed. Right-tailed. And two-tailed test. Okay, so those are the three types of tests. And as you're going to see, These tests are determined from the alternative hypothesis. So looking at the direction of the alternative hypothesis, we'll be able to determine what type of test it will be. So take, for example, if we have a not equals to, then it's going to be a two-tailed test. If we have a greater than sign, it's going to be a right-tailed test. And if we have a less than sign, it's going to be a left-tailed test. Good. So formulating hypothesis for mean. We've seen this already, but I just added more examples for practice. So a city mayor claims that the mean time spent by people in downtown parking spaces exceeds 33 minutes. So the claim here is that, so what's the claim? The claim is that the mean that the mean time spent by people is greater than 33 minutes. That's the claim. The opposite is simply that mu is less than or equals to 33. So given this, we can see that the opposite will be our null hypothesis, and the claim will be our alternative hypothesis. Okay, so start with writing what's the claim and what's the opposite, and then derive this next. Okay, so looking at this, my question for you is, what type of test would this be? Would this be right-tailed, left-tailed, or two-tailed test? Your guess is as good as mine. It's a right-tail test. So it's a one-tail, upper-tail test. Fantastic. All right, let's look at another example. So the Department of Agriculture has stated that average annual rainfall in a particular county is at least 23 inches. Here we have at least. It's at least. So what does that mean? We are saying that our claim here is such that the mean, remember we expressed this in terms of the population, so that the mean is at least, so which means it's greater than or equals to 23. So that's what the at least means. So at least, so greater than or equals to 23. So that means that the opposite will be mu is less than 23. So looking at these, our null hypothesis will be the claim, and our alternative hypothesis will be the opposite. Okay? Now, I usually tell people that we state the null hypothesis with an equal sign. So the null hypothesis is a statement of equality, so I can as well have written this as h of O is such that mu is equals to 23, and h of A is such that mu is less than 23. This is also correct. Either way is correct. Just remember that our null hypothesis is a statement of equality. Again, what type of test would this be? You are right if you said a left-tail test. So it's a one-tail, lower-tail test or a left-tail test. Let's look at one more example because I think you guys are getting to understand this whole concept. So the company that bottles a popular soft drink has set the filling machine so that the mean contents per bottle is equal to 12 ounces. So what we're saying is here is that our claim is that mu is equals to 12. And that means our opposite is mu is not equals to 12. I'm sure you knew that already. Cool. So looking at this, we can see that our null hypothesis is our claim. So this is going to be h of O. And our opposite is our alternative hypothesis. So there it is. Now, of course, you know the next question. What type of test are we going to conduct? That's right. It's a two-tailed test. Fantastic. So so now you have learned how to formulate the hypothesis, and you also learned how to determine what type of test you're conducting, because that would affect how we solve the problems. So when we are dealing with a two-tailed test, we simply have our rejection regions in both tails. So our alpha is splitted into two. This is alpha over 2. This is alpha over 2. It is different from the previous case. Take, for example, this is a left-tailed test. So our rejection region is right here. So this is where alpha is, not alpha over 2 this time around. So if this is our standard number distribution, our z-value will depend on what alpha is here, and our z-value here is dependent on this area of alpha divided by 2. And you know that this is symmetrical, so if this is positive, this is negative of the same value. So that's how we're going to determine the critical value when we are conducting our tests. Sweet. So the things that we talked about in chapter 8 is very relevant in this chapter. So they're all connected. So confidence interval, hypothesis testing, it's all about statistical inference. You have your population and you have the sample, and we want to estimate our sample. We want to estimate the population parameters from our sample statistic, such as X bar, and here we have mu, and we have P. So we want to be able to estimate. So this is where the inference comes in. We want to be able to estimate the population parameter from our sample. So this is our sample, take for example, and this is our population. So this is really the big picture of what we are doing of statistical inference. Okay, because I felt that we should still have more fun. So this is obvious. So looking at this problem, we can see that this we are saying here that a customer who buys pipes feeding from a supplier claims that the mean diameter of the two pipes is not equal to 2. So it's not equal to 2. So our claim is that mu is not equal to 2, and that means the opposite is that mu is equal to 2. So our null hypothesis will be the opposite. That is our null hypothesis, and our claim will be the alternative. Okay? All right, and you know that it's going to be a two-tailed test. Let's look at one more example. A pharmaceutical company has produced a new drug to treat heartburn. The company believes that the drug will stop heartburn in less than 15 minutes. So the company claims that the population mean is going to be less than 15. That's the claim. And the opposite here is that mu is greater than or equals to 15. So what that means here is that this will be our null hypothesis, and this would be our alternative hypothesis, and that's what we have here. So our alternative null hypothesis is the opposite, and our claim, alternative hypothesis is our claim. All right. Again, what type of test are we going to conduct? This is a less than sign, and so that means it's going to be a left tail test or a one tail lower tail test. That's how we call it. Sweet. Now you all have mastered the art of formulating hypothesis. Next, let's look at how to compute test statistic. Okay, but before we do that, let's look at the general picture of what we've been talking about in terms of, let's talk a little bit about the rejection region. So when we have a two-tailed test, I mentioned earlier that the rejection region is on both tails. So the rejection region is when we have the inconsistently large sample mean. And this other area here is the fail to reject region. So it's a fail to reject region. I'll call it FTR, fail to reject region, and then the rejection region. If we are looking at a one-tailed test, the rejection region is only to the right here. And again, this other region, this whole region here is a fail to reject region. Fail to reject region. Okay. So looking at this here, our null hypothesis here, we said that the mean is less than or equals to 100 and the alternative is that the mean is greater than 100. So if the sample mean is inconsistent, that is higher with the null hypothesis, we reject the null hypothesis. So if it's way high, above 120, somewhere around here, it's in the rejection region, basically. And the same goes with the left tail test, the same explanation. So this is the rejection region, and this other area is the fail to reject region. So this other area here. Okay, cool. So that's the general big picture that we're going to use in making our decision. You see, we are just building the foundation, and then we'll look at examples on how to really conduct a hypothesis test in several steps. But in all of this, you know, one thing which must take into considerations are errors that could occur when we conduct hypothesis testing. What sort of errors exist? So there are basically two types of errors that we might commit. So a type 1 error and a type 2 error. Now, if we reject the null hypothesis when the null is actually true, and we conclude that, let's say there was a treatment effect, what we are committing is a type 1 error. And if we fail to reject the null hypothesis, even though the null is false, this is called a type 2 error. And this is one of the errors that we really need to be mindful of. Okay? Now, if we reject the null hypothesis when it is, if we reject null hypothesis when it is false, that is good. If we fail to reject the null hypothesis, that is, do not reject null hypothesis when it is true, that is also good. So we can, this is a very simple 2x2 matrix. So a hypothesis testing error can be made if extreme sampling error occurs. And we want to minimize this. So it is always possible to make the wrong decision, but we can minimize that by, as we'll see, by a large sample size, when we randomize our sample, and when we implement some proper experimental controls, which is not something we're going to do in this class. All right, let's move on. So a type 1 error basically is erroneously rejecting the null hypothesis. Now, thinking you found something out of the ordinary when in fact you have not. So that's a type 1 error. So so for a type 1 error, we introduce alpha. Alpha is the maximum probability of making a type 1 error. So it's the amount of uncertainty that we want to introduce. So alpha is the probability of a type 1 error rejecting the null hypothesis when the null is true. So alpha it's the amount of uncertainty we are willing to live with when we reject the null hypothesis. So we typically set the value at the beginning of a study. So at the beginning of a study is when we set our significance level. The second type of error, which is the type 2 error, is, so a type 2 error occurs when the sample data results in a decision to not reject a false null hypothesis. Okay, so a type 2 error is not rejecting the null hypothesis when you should. So it's not rejecting the null hypothesis when you should. So not realizing you have found something out of the ordinary when in fact you have. And this is something that researchers or politicians hate to make these types of error, you know. So we use beta to represent the type 2 error. So this is the probability of making a type 2 error. So that's beta can be computed for any value of population mean that makes the null hypothesis false. Okay, so beta is the probability of a type 2 error not rejecting the null hypothesis when you should reject it. Okay, so we do not set this value at the beginning, unlike alpha. We do not set beta at the beginning of a study. Beta depends on alpha. So beta depends on alpha, the significance level, and on the value of a parameter you are testing, as well as on, it also depends on the population standard deviation and the sample size. Okay, we won't really go deeply into computing beta, but one thing I want to say in general is that knowledge is power, okay? And determining the power of our test is very important. So they say that more data is equals to more information, and that is also equals to more knowledge. So the more data you have, the more knowledge you have, and that means the more power you also have. So the higher the tendency of making an error. So yeah, so knowledge, as again we know, comes from experience. So the experience is what helps us to generate this data that we use in our analysis. Okay, so power is the ability to correctly reject the null hypothesis. So if we're going to look at that, which the power is actually equals to 1 minus beta. All right. We've talked about the significance level, alpha, so the maximum allowable probability of committing a type 1 error. So when we're starting a study, we need to set what our alpha value is, and that will enable us to determine our critical value, which we put here as a cutoff, and that's what we would use in making our decision. If our test statistic that we're going to see how to compute soon is in the rejection region, then we will reject the null hypothesis. Otherwise, we fail to reject the null hypothesis. So the probability of committing a type 1 error is equals to alpha. So this is our decision rule here. The decision rule is that if we compute a test statistic and and our test statistic is to the right of the critical value, then we would reject H of O. Otherwise, we fail to reject H of O. Or we can also look at in terms of the sampling mean. If it's greater than the cutoff, then we reject. Otherwise, we fail to reject. So these are three approaches in conducting hypothesis testing. We are going to look at the p-value approach, and we are going to look at the critical value approach today. All right. So let's look at, so finally we can get to solve several problems. So in this problem, again, sigma is known. Just like we saw in confidence interval, we're going to look at a case when sigma is known and when sigma is unknown for the mean. For the proportion, we don't have the case of whether sigma is known or unknown. It's always z. Remember, when sigma is known, then our test statistics will be z. If sigma is unknown, then it's going to be t. But anyways, let's read this question and see how we can interpret it based on all that we have covered so far. Are you ready? Okay, so here's a problem. A home building company wishes to test whether the mean time to frame and roof a new home is 25 or fewer days. So that is what we want to test. So our claim here is, what's our claim? Is that mu is 25 or is less than or equals to 25. That's the claim. Now the opposite is mu is greater than 25. Okay, so which means our null hypothesis would be mu is less than or equals to 25, and our alternative hypothesis will be mu is greater than 25. Exactly. So with these, we know that we'll be conducting a right tail test. Okay, if someone asks you what is mu, you get mu from the null hypothesis. Remember, it's a statement of equality. That's why I like to write it as mu is such that H of O is such that mu is equals to 25. So you can already see it clearly from the null hypothesis that mu is equals to 25. Now, what are we given in this question? We're given the standard deviation, sigma, is known to be 3 days. Alpha is 0.1, and n is 64, and a sample mean of 26 days. So that is our x bar. So what conclusion should be reached? Should we reject the null hypothesis, or do we fail to reject the null hypothesis? So what we're going to do here is compute the test statistic, and our test statistic is computing our z, and you all remember how to compute z. Remember that z is, for a sampling distribution, is equals to x bar minus mu divided by the standard error, sigma of x bar. And recall that sigma of x bar is equals to sigma divided by square root of n. Okay? So that's how we determine z. And so here is a test statistic. Let me take this off. So here's a test statistic. So I will just put in this to remind you of what we've done in the past. And so that's how we got this. And we have 26 minus 25. 25, you got it from here. And the standard deviation is 3 divided by square root of n, and n is 64. If you do the computation, you should have 2.67. So our test statistics is 2.67. Now we're going to compare 2.67 with a critical value. What is our critical value? that will be z of alpha. And alpha here, that is z of 0.1. How do we get the z value? So we're given that alpha is 0.1. What we're really saying is that we have this distribution, the right tail. This area is 0.1. What is the z value when that area is 0.1? I will do a quick review because I know many of you like review, and I'm going to bring up Minitab again to show you how to do this in Minitab. I have also shown you how to do this with your table. Well, let's look at Minitab once more. So here is Minitab. Again, you go to graph, probability distribution plots, view probability, okay. We're looking at the standard normal distribution because we're trying to find z critical value, shaded area, right tail, and what did we say is alpha 0.1. Okay, and then you click OK, and you have it there that the test statistic, the critical value is 1.282. And our test statistic is greater than the critical value. So which means our test statistic is in the rejection region. So our decision would be to reject the null hypothesis. All right, so 1.282. That's what we get from Minitab. And here is the distribution. So 1.28 to two decimal places 1.28. So we have that z of 0.1 is equals to 1.28. Okay. And since our test statistic is in the rejection region, it implies that we are going to reject the null hypothesis since the test statistic is greater than the critical value. So that's the decision to reject the null hypothesis. Okay. So how do we interpret this? So to interpret this, we'll say there is enough evidence to support the claim that, and then you state what the claim is. Okay? So there is enough evidence to support the claim that the mean time to fame and proof a newborn is 25 or fewer days. Okay. All right. And if we had failed to reject, they would say there is not enough evidence to support the claim. Let's look at another example. And in this example, we would have a case whereby, so the first thing again always is to state the null hypothesis and your alternative hypothesis before you go ahead. So the company that packages oatmeal uses an automatic filling machine that is set so that the mean fill volume is 16. So we are saying that our claim, is such that mu is equal to 16. The opposite is that mu is not equals to 16. So what that means is that our null hypothesis is such that mu is equal to 16, and our alternative hypothesis is such that mu is not equal to 16. So which means we'll be conducting a two-tailed test. So the machine has non-standard deviation. So non-standard deviation, so which means that we'll be computing the z statistic. If we do not know if sigma is not known, which we'll look at next, we will be computing a t statistic. So here we'll be computing a z test statistic. So we have sigma is 0.422. So let's just look at the solution. So we have the point estimate is given as 16.2 16.2, that's the sample mean, X bar. Mu is equals to 16. Sigma is equals to 0.422, and the random sample size is 14. Okay, it's 49. And so with these, our test statistic is 3.32. We are going to compare our test statistic with the critical value, which depends on what our significance level is. So we are here again using a significance level of 0.1, but the difference here is that we are looking at a two-tailed test. So which means that our critical value is Z alpha over 2, splitted into 0.1 is splitted into both tails. Let me bring up Minitab to show you how to determine the critical value, because it's going to be different from the previous example. So in the previous example, this was right tail, and our critical value was 1.282. Now we have both tails. Let's bring out the last operation, shaded area. We are going to use both tails, and our alpha will be split into both tails. So one tail will be 0.05, the other 0.05. Our critical value is 1.645 and negative 1.645. What that means is that if our test statistic is less than the critical value, which means it's in the rejection region to the left, we will reject the null hypothesis. Or if our test statistic is greater than 1.645, which means it's in the right side, it's in the right rejection region, we would also reject our null hypothesis. So that's the difference. You can see this is 1.645. The other was 1.282. So be very mindful. This is a right-tailed. This is a two-tailed test. Awesome. So with these, we can see here, and let me erase that. How did that come in? Okay. All right, get back to there. Okay, good. So as we can see here, our critical value is 1.282, and our test statistic is to the right of it. So it's in the rejection region. So our decision will be to reject the null hypothesis. So it means that there is enough evidence to support the claim and you state what the claim was. All right, fantastic. Now, so what I've shown you here is using what I call the traditional method, or the critical value approach in making decision. So the critical value approach. Next, I'm going to show you how to also make this decision using the p-value approach, which means that after computing a test statistic, we will determine what the alpha value is of this test statistic, and then compare that alpha value with our significance level in order to make our decisions. All right, so the p-value approach. The p-value is the probability of obtaining a test statistic at least as extreme as the test statistic we calculated from the sample. So the p-value is also known as the observed significance level. Okay, so that's the p-value. So it's also called a probability. So it's a probability associated with a test statistic. And we've been computing the p-value for a very long time. You know, given z, determine the area. That area you've been determining, you've been solving for using Minitab or the table or the calculator is the p-value. So it's the probability associated with the test statistic. Okay? If the p-value is less than the significance level, we are going to reject the null hypothesis. Otherwise, if the p-value is greater than or equals to the significance level, fail to reject the null hypothesis. That's the decision we're going to make. So here's an example and the whole solution given there using the p-value approach. So I'll just quickly go dive. This is something we've done before. Remember, we found that the test statistic is 3.32. So what you're going to do is determine the p-value associated with this. And since it's two-tailed, we multiply it by 2. So the area here is 0.0005. And you multiply that by 2 to determine the p-value. And you compare that p-value with alpha, which is 0.1. And since the p-value is less than alpha, we reject the null hypothesis. All right, now, before someone asks me, how do you determine the area again given z? I'm going to show you once more in Minitab. So our z is 3.32. Let me bring up Minitab. Go back here again, and we say using the standard normal distribution. But this time around, instead of probability, we change it to x value, but our x value means our z value, okay? And we are looking at a two-tailed test, right? No, we're trying to determine the area given that z is 3.32. And we can use the right tail. Just see what I'm going to show you first. And so if we click on right tail and we say this is 3.32, that's the z. When you click OK, that gives you the area here to the right, which is 0.00045101, and this is approximately 0.0005. Okay, that's what I have in the text, 5. And then you multiply that by 2 since it's a two-tailed test. So this is alpha over 2 here, alpha over 2 to the right here, and that gives you the p-value. I hope that is clear. Okay, so that's how to determine the area given z. So given z, find the area. Cool. And so that's what we did in order to make our decision. All right, let's look at another example. So in this example again, now in this case, sigma is unknown. So when sigma is unknown, I said we're going to determine the t statistic. Now it's not z, but t. So what's the difference here? The difference here is that we're going to compute our test statistic will be a t statistic. So which means that in order to determine our decision point, our critical value, like we did in the previous chapter, we'll determine what the degree of freedom is, what the confidence level is, or this time around the alpha value to determine the critical value. And I will show you again once more in Minitab. So looking at this question, the quality manager at a fast food outlet wishes to test whether the mean volume for milkshakes is 16 ounces. So what we're saying here is that the claim is that mu so our claim is that mu is equals to 16. Our opposite is that mu is not equals to 16. So which means that this is going to be a two-tailed test. Our null hypothesis is our claim. Our alternative hypothesis is our opposite. So to do so, she randomly samples 16 shakes and observes that the sample mean, so that's X bar, is 15.93 ounces with a sample standard deviation, that's S. I mean, that's sample standard deviation, yeah, that's S is 0. So S is equal to 0.5. Using an alpha level of 0.1, so alpha is equal to 0.1. So if alpha is equal to 0.1, we would, how do we determine the test statistic? I mean, how do you determine the critical value? That's the T critical value. And so we'll look at that. All right, so given all that we have here, we can determine the T statistic. So the T statistic is basically X bar minus mu divided by the standard error, which is S over square root of n. So with what is given, we can compute this. So that's the test statistic. But what we need to know next is how to determine the critical value. So this value, how do we determine it? So we are given that alpha is 0.1, and we are also given that n is equal to 16, so the degree of freedom is n minus 1, which is 15. Okay? So if you bring up Minitab, we would, let's go back to the last operation, but this time around, change this to T, not normal, but to T, and our degree of freedom is 15. Go to the shaded area. We're looking at a two-tail, so both tail, but change this to probability first, because we're going to enter the alpha value, and alpha is 0.1, and then click OK. And when you do that, you can see that the T critical value is 1.7530. If you check the table, you have 1.7531. So it's approximately the same. Cool. That's how to determine the T critical value rate using Minitab. Fantastic. All right, so with that, we now compare our test statistic of negative 0.56 with our critical value. And as you can see, our test statistic is in the fail to reject region. So since our test statistic is in the fail to reject region, do not reject the null hypothesis. Our test statistic is not in the rejection region. Okay, so how do we interpret that? It means that there is not enough evidence to support the claim that the mean volume of milkshake is 16 ounces. That would be the interpretation. Remember, as I said, I always love you to write out the interpretation, not just solving the problem, but what is the interpretation? So if you're rejecting the null hypothesis, we state that there is enough evidence to support the claim that, and then you state what the claim is. If you fail to reject the null hypothesis, then you're going to express it, your interpretation this way. There is not enough evidence to support the claim that, and you state what the claim is. Good. So let's move on to the next section. So hypothesis test for a proportion. So far, we've looked at hypothesis test for a mean when sigma is known and when sigma is unknown. Remember, for proportion, we are always only going to compute what? A z statistic. There's no t statistics in proportion, always z. So proportion, we go the z way, not t. Okay, so the null and alternative hypotheses are stated in terms of the population parameter p, not mu this time around. The sample statistic is p hat. The null hypothesis should be a statement concerning the parameter that includes the equality The null hypothesis is a statement of equality. The significance level of the hypothesis determines the size of the rejection region. That's alpha. So this is just a repetition of what we've said already. The test can be right-tailed, left-tailed, or two-tailed, depending on how the alternative hypothesis is formulated. So here are some examples. If we have our hypothesis this way, we know this is going to be a two-tailed test. This is a right-tailed test, and this is a left-tailed test. And you can see this is stated in terms of the population proportion, so P. Cool. All right. So hypothesis test for a proportion involves categorical values. So here we have two possible outcomes. Success possesses a certain characteristics. Failure does not possess a particular characteristics. And here's an example. So we have customers like or don't like a new product. Items manufactured are defective or non-defective. Okay. So here are the steps in conducting hypothesis tests for a proportion. The first step is that you specify the population parameter of interest. Next step, you specify the null and alternative hypothesis. Next step, you specify the significance level. Next step, you construct the rejection region. So for a one-tailed test, you determine the critical value to be Z alpha. For a two-tailed test, it's going to be Z alpha over 2, similar to what we've done so far. And then the next step, we compute the sample proportion. We compute the test statistic. So that is the test statistic. Remember for Z. This is similar to what we saw in the last chapter for finding Z. Nothing has really changed. And we determine, so given our test statistic, we determine the probability that is associated with the test statistic, which is our P value. And we use our P value, we compare the P value with alpha in order to draw a conclusion, whether to reject the null hypothesis or fail to reject the null hypothesis. All right, my friends. So let's look at an example. So here we have a company claims that the proportion of dissatisfied customers is less than 0.1. So what the company is saying that the claim, outputs for C, is that P is less than 0.1. That means the opposite is such that P is greater than or equals to 0.1. So that means that our null hypothesis is such that P is greater than 0.1, and our alternative hypothesis is such that P is less than 0.1. So looking at these, we can see that we'll be conducting a left-tailed test, okay, since the sign for the alternative is less than. All right, now what else are we given? To test a random sample. Remember, one of the requirements we really want to have here is that our sample, our evidence that we're gathering is random, okay? So a random sample. That way we can minimize bias. So the sample size is 100 customers is selected and 6 are dissatisfied. So 6 are dissatisfied, so that is X is equals to 6 and is equals to 100. So that means our sample proportion will be X over N, which is 6 divided by 100. Okay. That's, as you're reading through, you can start writing out what you understand. So using a significance level of 0.05. So alpha is given of 0.05. So when we compute that this test statistic, we're going to compare it with alpha. So conduct the hypothesis test using the z-test statistic approach, or I could say using the critical value approach. All right, here are the steps. So we have seen this. This is our hypothesis, and alpha is given. And now we computed our sample proportion. Now with these, we can go ahead to determine the standard error, sigma of p hat. And so when you compute that, you have sigma of p hat is 0.03. And so now we can determine z. What is z? Z is equals to p hat minus p divided by the standard error of p hat. Okay? So that's p. Similar to what we did in the last chapter. Okay. So we want to compute this z, and now we're going to use this from after knowing our z, we determine the probability associated with our z before we make a decision. So next, looking at the slide here, these should be negative 1.645. I will explain. Okay, next we determine our z, and when you do the computation, you have that z is negative 2. Okay, so that's the test statistic. Now we know we're looking at the left tail, and this is the rejection region. This is 0.05. So the question is, what is the z value associated with alpha of 0.05? So this point here would be our critical value. So this is the rejection region. This is the fail to reject region. Okay, so to determine this, since this is 0.05, I would go on to Minitab again just to show you all, so that by now you've all mastered the art of determining the critical value. So let's go back here again to the last operation. Change it back to normal. Let's become normal. And ensure that the mean is 0 and 1. That's a standard normal distribution. Go to shaded area. And this time around, we look at left tail. And what is the area? What's alpha? Alpha is 0.05. And then you press OK. And you can see that the critical value is negative 1.645. Great. So negative 1.645. And we're going to compare our z to this. Now, as you can see, our z is negative 2. It's to the left of the critical value. So since our test statistic is less than the critical value, we will reject the null hypothesis. So we would reject the null hypothesis, which means there is enough evidence to support the claim, and you state what the claim is. Great. That's really all. That's really how to conduct hypothesis testing. We have seen how to conduct hypothesis testing for the population mean when sigma is known and when sigma is unknown. We've also seen here how to conduct a hypothesis test for proportions. So that's pretty much everything. And in the last section, I will just generally talk about the types of errors. So let's talk a little bit about type 2 errors. Great. So a type 2 error occurs if a false null hypothesis is accepted. Hypothesis is accepted. And the probability of a type 2 error is given by a symbol beta. Now, alpha and beta are inversely related, but are not proportional. Okay? Now, a type 2 error, like I said earlier, is not rejecting the null hypothesis when you should, and so not realizing you have found something out of the ordinary when in fact you have. Okay? Now, the beta is the probability of a type 2 error not rejecting the null hypothesis when you should reject it. So, and then I talked about the power of the test. So usually, the power of the test is the probability that the hypothesis test will correctly reject the null hypothesis when the null hypothesis is false. And this is a general expression for it. So when we determine beta, we can determine the power. And we also talk about the power curve. So it's a graph that shows the probability that the hypothesis test will correctly reject a false null hypothesis for a range of possible true values of the population parameter. In this class, we won't look at computing beta. In my Statistics 2 class, I will show you how to compute beta and how to compute the power. We'll look at more example then if you're taking Stat 2 with me. Great. So far, what have we talked about in terms of errors here? We want to control for alpha and beta. Now, hypothesis testing is subject to error. So there are two possible errors, as we've seen. You can commit a type 1 error, or you can commit a type 2 error. So there are adverse consequences associated with each type of error. And we want to ensure that we minimize committing any error. So costs of different kind usually are involved in either a type 1 error, that's alpha, or a type 2 error, that's beta. Now, hypothesis tests should be conducted accordingly, so according to the cost of these errors. So this is the general conversation. So far in this video, we have seen how to conduct hypothesis tests for the mean when sigma is known and when sigma is unknown. And we've also seen how to conduct the hypothesis testing for proportion as well. So that's pretty much everything. So with this, we've come to the end of chapter 9. Fantastic. Yay. So I wish you all a beautiful rest of your day and see you all in the next video. Bye for now.